Over the last century, research into the brain's physical mechanics has accelerated rapidly, uncovering more about how the organ functions than any prior era. This surge in discovery is tied to fMRI technology, capturing localized brain activity and translating it into the precise digital slices shown here. These imaging breakthroughs supported the rise of a hybrid field, educational neuroscience. This field was driven by the idea that mapping learning in the brain would reveal scientific truths that educators could apply directly to their practice. This led to an attempt to bypass traditional psychology, trying to translate laboratory imaging data directly into the design of digital learning platforms. However, taking the results of a brain imaging study and applying them directly to educational practice is scientifically unviable. Laboratory neuroscience relies on highly controlled settings where researchers can manipulate individual factors to determine specific cause and effect relationships. Classrooms, both physical and virtual, are different. They are complex environments, saturated with noise and uncontrolled contextual variables. This mismatch explains why applied educational technology research rarely makes mention of fMRI data. While brain scans identify raw physiological mechanisms, they do not measure the holistic learning that occurs in a classroom. Cognitive scientist John R. Anderson described this structural barrier as the 7 orders of magnitude problem. This scale shows how observation changes. At the bottom, a neural firing occurs over milliseconds. In seconds, we observe working memory. In hours, we reach course sessions. At the peak, professional education takes years, integrating millions of smaller events. Data gathered at the millisecond scale provides no actionable information for a system that functions over several years. To bridge these 7 orders of magnitude, engineers must build intermediate theoretical and physical connections. Without direct brain mapping, the challenge is finding a way to scientifically measure the mind within digital settings. This is done through intermediate proxies, the conceptual links between a neuron firing and a student's interaction with software. We start with the physiological limits of attention and working memory established in the lab. Researchers then translate those limits into applied models, such as cognitive load theory. This theory provides rules for instructional design based on mental capacity, allowing engineers to account for the brain's limits without tracking every cell. Effective educational software is built by tracking these theoretical constructs rather than raw neurobiology. While constructs provide a framework, digital environments still need real-time data to inform their design. This is where psychophysiological proxies come in, unconscious physical outputs that indicate internal cognitive states. Early methods of capturing data were physically restrictive. This vintage EEG setup required wired sensors and a chart recorder that anchored the subject. Similarly, early gaze tracking used bulky manual equipment that restricted a student's posture and prevented natural learning behaviors. Modern research uses a multimodal approach, combining EEG and psychophysiology to assess cognitive load invisibly while students interact with educational video. One modern proxy is pupillometry. Researchers use changes in pupil diameter to track reading strategies. The contraction and expansion provide a marker of cognitive processing. Gaze tracking patterns map how a student's eyes move across a complex problem-solving interface. These specific visual patterns allow algorithms to detect the exact moment a learner becomes confused. The final layer of this translation is learning analytics. Analytics consolidate these data streams to trigger interventions that support a student's motivation and self-regulation. These proxy measurements are the actual bridge between cognitive science and educational technology. Building effective educational technology requires more than porting brain scans into user interface design. This shift in focus marks a maturation of the learning sciences. The process follows a specific chain of translation, starting at the base with biological foundations. This foundation is translated into psychological theories, like those governing working memory. The next layer adds methodologies, using proxies like pupillometry and gaze tracking. The stack is completed by learning analytics. This complete chain allows researchers to study learning holistically while spanning vast orders of magnitude. Respecting this translation process is necessary to realize the goals of educational neuroscience without hype. Ultimately, advancing the future of digital education depends entirely on engineering this specific, proven path out of the laboratory.